In 2.5, the rational root theorem. So I'll read the definition for the rational root theorem. If the polynomial p of x has integer coefficients, then every rational root of the polynomial equation p of x equals 0 can be written in the form p over q, where p is a factor of the constant term of p of x and q is a factor of the leading coefficient of p of x. So the formal explanation is a little bit confusing, but I promise it's not too bad. So where it says that p is a factor of the constant term, that's this term here in our first example. Because it's a constant, there's no variables attached to it. And q is a factor of the leading coefficient. The leading coefficient is just the first coefficient of the first term. So p equals 25, because that's the constant here, and q equals 6 because this is the leading coefficient. But it's asking for the factors of both of these. So we'll list off all the factors of 25. We know that that's 1, 5, and 25. 5 times 5 is 25, 1 times 25 is 25, and 25 times 1 is 25. In this instance, because there's a 5 times 5, we only need to write 5 once. And for q, we'll list all the factors of 6. So 1 times 6 is a factor, 2 times 3 is a factor, and that's it. So now to find all the possible rational roots of this function, we'll list all these factors of p over q. And these are going to be both the positive and negative results. So we'll start out. Positive or negative 1 over 1. So this term and this term. And positive or negative 1 over 2. We have positive and negative 1 over 3. Positive and negative 1 over 6. So using this first factor of p, we're going to go through all the factors of q. In our second term, 5 plus or minus 5 over 1 plus or minus 5 over 2 plus or minus 5 over 3 plus or minus 5 over 6. And lastly, we'll use 25 as our value of p. 25 over 1, positive or negative 25 over 2, positive or negative 25 over 3, and positive or negative 25 over 6. Now there's no duplicates for this example because each of these are already simplified. So we count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 that we count, but both of those have a positive or a negative value. So it's actually 12 times 2. So there's 24 possible roots for the first example. So for the second example, we know that p is our constant. Our constant in this example is 64. Q is our leading coefficient, which is 4. We're going to list all the factors of 64. So that's 1 times 64, 2 times 32. There's no, 64 is not divisible by 3, but it is divisible by 4. 64 divided by 4 is 16, and 8 in the middle. 8 times 8 is 64. Now for our q value, we have 1 times 4 is 4, and 2 times 2 is 4. we'll have plus or minus PQ, or P over Q, and so that's equal to 1. So that's equal to positive or negative 1 over 1. Because we're focusing on this term here. This term over all of these. So plus or minus 1 over 2, positive or negative 1 over 4. And we can move on to the next one. Positive or negative 2 over 1, positive or negative 2 over 2, positive or negative 2 over 4. To the next one, 4, positive or negative 4 over 1, positive or negative 4 over 2, positive or negative 4 over 4. Now that I've hoped that you guys understood the general process of this, I'm going to go ahead and skip to the end once I've written out all the fractions of P and Q. Here's all of the fractions written out, but we need to cross out duplicates. So some of these fractions we know that we can simplify further. So I'll go ahead and cross out ones that are the same. For example, positive or negative 2 over 2 is just 1, which we already have. And positive or negative 2 over 4 is just 1/2, which we also already have. 4 over 2 is 2, which we already have here. 4 over 4 we already have here as 1. 8 over 2 we already have as 4 over 1. 8 over 4 we already have as 1 over 2. 16 over 2 we already have as 8 over 1. 16 over 4 we already have as 4 over 1. 32 over 2 we already have as 16 over 1. 32 over 4 we already have as 8 over 1. 64 over 2 we already have as 32 over 1. 64 over 4 we already have as 16 over 1. So that dwindles it down a little bit. So now we have 1, 2, 3, 4, 5, 6, 7, 8, 9 fractions, but they each come in a positive and a negative. So we have 18 possible roots. This process is a little bit tedious, but it's not too difficult. Now that we have these lists of possible roots, we need to find out if it's an actual root. So we'll use synthetic division as learned in the last video and find a remainder of 0. Remainder of 0. If we find a remainder of 0, we know that that possible root is an actual root. So we're going to test the polynomials for the given root. We'll write the new polynomial that is found, factor it, and solve. So the root they've given us is x equals 2. So we can write x over here is the root and bring down these coefficients. We're not missing any terms, so we don't need any zeros as placeholders. And we'll continue synthetic division. 15 times 2, negative 30, and 0. Since we found a remainder of 0, we know that 2 is a root. Now, if you're lost on this synthetic division, the last video went over that, so you can refer back there for extra help. So we can rewrite these coefficients in a proper expression. X to the power of 2 minus 2x minus 15. We can factor this by hand. We'll set up these two brackets. So looking for a value that's going to add up to -2 and multiply to -15. X plus 3 and x minus 5. So because x equals 2 is a root, we know that the opposite of x minus 2 is a factor. So x to the power of 3 minus 4x to the power of 2 minus 11x plus 30 factors out to x minus 2 times x plus 3 times x minus 5. And we know that that's also equal to 0. And when we set these factors to 0, our roots are x equals 2, x equals -3, and x equals 5. So our roots are 2, -3, and 5. And our list of possible roots would look like p over q. So p equals 30, as that's our constant here, and q equals 1, because the leading coefficient is 1. So the factors of 30 are 1, 2, 3, 5, 6, 10, 15, and 30. And the factor of 1 is just 1. Anything over 1 is just itself, so plus minus all of these numbers here are your possible roots. And of these possible roots, 2, -3, and 5 are the actual roots of this polynomial.